Perfect. Good afternoon, everyone. Welcome to the CISR seminar for this fifth edition of this semester. We have had 4 in the past, and there is 1 left for us to do. I hope you're doing well and you are staying strong in this semester where the break comes quite late. Today, I've got the great pleasure of having a colleague, Feng Hao Liu, be our speaker. Feng Hao is an associate professor with the School of Electrical Engineering and Computer Science on the computer science side, and he joined WSU in 2023, just this semester. He is not right now in the US, he's overseas, but thankfully this is virtually so he could join us. So Feng Hao is an expert in cryptography. His areas are wide, and he works on post-quantum and lattice-based cryptography, fully homomorphic encryption, and very many other things on fundamental cryptography. And today he would be marrying 2 important topics, cryptography and how things would change in the presence of quantum computing. I am very much looking forward to what he has to say. When he's back in the spring, he will be teaching CPTS 327. For those of you who are in computer science or cybersecurity, that is a required course that everybody takes, and that's fundamentals of cybersecurity and cryptography. That will be a course that he will be teaching in the spring. So the way this would work is we'll give him all the time now to present and save a little bit of time towards the end for Q&A. But if you have questions, I would be monitoring the chat. You can put them in the chat. Other than that, you could ask when the time comes in the end. So without any further ado, Feng Hao, welcome, and you can start presenting.
Thank you for the kind introduction. So today, as the topic says, I'm going to talk about cryptography in the presence of quantum computing. And in the next 30 to 35 minutes, I'm going to talk about, share with you some new opportunities and research directions. So we first start with an important motivation. We know Internet technology has revolutionized the world, transforming the way how we live, learn, and work. So by building a connected world, we have a lot of wonderful applications like online mobile banking, email, social media, and thanks for the online conference technology, we can still connect with each other, even if I am abroad. So security of cyberspace is always very important. Particularly, there are 2 important must-have features, privacy and authentication. And there can be a lot of sensitive data in the cyberspace. Consider the following example. A user wants to download her bank statement from the bank server. Certainly, she doesn't want the adversary to be able to see her balance or transfer unauthorized funds from her account. And there can be a lot of serious consequences if security goes wrong. For example, one instance when Zoom was first launched, because of security issues, it was banned for the government and universities. So fortunately, Zoom fixed the issues, and then so that we can still use Zoom today. So an important technology to protect internet security is public key cryptography. So it is the foundation of HTTPS, and it has been used to protect our email, secure payments, social media logins, and much more. And today, this HTTPS is used more often, or much more often than the original non-secure version of HTTP. So the foundation of public key cryptography relies on mathematical problems that are not solvable by even supercomputers. And very fortunately, we have a few candidates, such as factoring and discrete log. So without going into the details of those problems, but I just want to mention that these problems are not only of theoretical or mathematical interest. They have been deployed into crypto systems that are widely used. And because of their theoretical and practical impacts, 2 Turing Awards, which are the most prestigious awards in computer science, were given to the inventors of those RSA crypto systems and Diffie-Hellman key exchange. So, but the foundation is challenged. So in 1994, Peter Shor, a professor at MIT, he introduced a new polynomial time quantum algorithm to solve factoring and discrete log. So what does this imply? This means quantum computing is more powerful than classical computing. So if the adversary can build a quantum computer or a large enough quantum computer, then he can solve the factoring and discrete log and can also break the RSA or Diffie-Hellman key exchange. So fortunately, the technology was not there. So in 2001, the best factoring example by quantum computer is 15 equals 3 times 5. And certainly this is not, it's just way too easy. This instance is just too easy. And at that time, quantum computers are not scalable. So it was not practical yet. And however, the technology advances. Today, many companies and academia are trying to build larger and larger quantum computers, including IBM and Google. So let me share with you a time frame. So in 1998, we had a 2-qubit system. And over the next almost 20 years, the number has increased to 49. And in 2019, Google built a 53-qubit system and demonstrated for the first time a term called quantum supremacy. And this means for a particular sampling computational task, quantum computing can have significant, can perform significantly faster than classical computer. And this is not a universal quantum computing, but it's just for this particular task, we can already see a faster phenomenon by quantum computing. And the number of qubits is increasing. And so we think towards 2023, the number, 2030, the number like say can or might increase to 1 million. So, oh, by the way, the number of qubits is like one measure of the scale of quantum computers. Okay, so even though this projection is still like maybe hypothetical, but we need to prepare to face this new reality. So particularly, NIST, National Institute of Standards and Technology, they had this post-quantum cryptography standardization call back to 2016, and this is still an ongoing effort. And industry has participated in a lot of efforts in evaluating performances of several post-quantum candidates. So this includes Google or Amazon and way more. So we know traditional public key cryptography is facing a crisis because it will become obsolete eventually at some point. So we need new security infrastructure. So now it is a critical time to develop new sciences in between cryptography and quantum computing. We need new foundation for post-quantum crypto. And beyond that, we are also exploring new advanced crypto capabilities along the research of post-quantum cryptography. So my research, so the basic mission is to rebuild basic crypto tools against quantum computing. So this is this aligns with the post-quantum standardization call from NIST. And also, this will have significant impacts for future security of internet applications. And using this foundation, my vision is to enable much more efficient, say, richer crypto capabilities. So this would include computing on encrypted data, which is known as fully homomorphic encryption, and applications to private machine learning and data analytics. And there are a lot of still numerous new advanced crypto designs. So today, I am going, my talk is structured in the following. So I will talk about very basic backgrounds so that you have a sense about what crypto research is about, and a little bit about my work and my vision. So let's talk about the background, the very fundamental crypto basics. So in general, cryptography asks the following two important what and how questions. What is security and how to achieve security? So intuitively, we want no attacker can break the system. But this term is still a little bit too vague. So what does this mean? Can we make the say definition more precise? And how to achieve security? This is also another very say broad question, because there can be infinitely many possible attacks. So how can we defend against infinitely many possible attacks? So the modern cryptography has developed the following, say, approach, a scientific approach. So first, we would like to define a very clear security goal. For example, consider we want to build a secure channel. So usually, so by building a security channel, so what does a secure channel mean? So usually we use a kind of picture to demonstrate this. Consider there is a sender and there is a receiver. So they want to communicate securely, and hopefully there is a secure channel for them to send private messages. So intuitively, what they want is if there is an adversary listening to the channel, the adversary cannot figure out what they are talking about. So this is kind of the big idea we want to capture. So modern cryptography, we want to define security. What does that mean by the adversary cannot figure out anything or figure out what they are talking about? So we need to formulate a notion that captures secure channel. So so before, people were trying to use this notion where the adversary cannot recover the whole plain text. So is this notion, this idea good enough? So for example, if the user wants to send this message, say, help me Obi-Wan Kenobi, you are my only hope. So if the adversary can say, even if say the adversary cannot figure out the whole message, but if he can figure out a partial message, but in this example is Obi-Wan Kenobi, then we consider this thing as not secure enough, right? So because by figuring out this, the adversary might already know something. So what we really need is the attacker cannot learn anything. And this idea and was like formulated and was proposed by Goldwasser-Micali. So how do we capture the idea about cannot learn anything? So we consider this orange message as the real message sent by the sender. And we consider another imaginary dummy message. And this dummy message can be anything, okay? Empire is the best, or how are you today? Something like this. And security requires that the adversary cannot distinguish whether the message was sent in orange or in blue by just listening to the channel. Okay, so this indistinguishability requirement is very, very important. And if this requirement is achieved, then we can argue that the attacker cannot learn anything. And this notion was explicitly requested in the NIST post-quantum cryptography call. So back to 1982, over the almost 30 or 40 years of studies, and this notion will be used, is used and will be used in all of the future and current standardization. Okay. So the next question we ask is, how do we realize the security goal, the secure goal? So first we note there might be no real physical secure channel because maybe these two parties are far away. And in this scenario, they might be across the the galaxy or whatever. But in the real world, people might be a long distance, across the Earth. So no practical physical secure channel is assumed in this picture. So the idea is we want to construct a droid, and this droid is known as encryption using mathematical objects. So intuitively, the encryption encapsulates the message. And for those who have the secret key, they can recover the message. On the other hand, for those who do not have secret keys, like adversary, he cannot distinguish whether the encapsulated message is orange or blue. Okay, so now we want to answer the next question. How can we prove security against infinitely many attacks? So modern cryptography has developed the reduction framework. So this framework consists of several components like hard mathematical problems, design, and reduction. So let me show you with this picture. So we have one or multiple hard mathematical problems, and we designed one crypto system based on the mathematical problems, and we would like to build a reduction. So what does the reduction mean? So you have learned maybe about this NP complete and NP reduction. So this idea is very, very similar to the NP reduction, that you transform mathematical problems into these crypto systems such that if you want to, we want to show that if an adversary can break the crypto system, then there exists a reduction or another algorithm that uses the adversary can solve the mathematical problems. Okay, so the equivalent statement is, if the mathematical problem is not solvable, then no adversary can break the crypto system. Implies the crypto system is secure. Okay, so very fortunately, we have some candidates, as we mentioned in the very early. So for example, RSA problems and discrete log problems. So people have already used these mathematical problems to build secure crypto systems and develop reductions. So in the quantum era, so we can think of this quantum computing as a very powerful killing tool that it can eliminate the hard mathematical problems like RSA and discrete log. So how can we defend against this? How can we rebuild crypto system? So we notice that this reduction framework also holds in the quantum era, but all we need is a new hard math problem that is hard also for quantum computing. And of course, we might need new crypto designs and proof of security. So basically, this is what post-quantum cryptography is like trying to work out. So let's talk about this NIST post-quantum core. So the goal of NIST is to standardize future post-quantum cryptography, and this effort has begun in 2016, and it is still a current effort. So according to NIST, say migration from one system to another might take more than 20 years. So it is harder and it takes longer than what we might think about. So there are a lot of challenges because, say, it might be very hard to find plausible math problems. And even if you find those math problems, you need to we need to research on the parameters, concrete parameters, efficiency, security, and also we need to implement those, say, hardware implementation, software implementation, and then we need to deploy the crypto system into our real world. So, say, currently, there are some hard math problems studied by the community. So there, for example, code-based, lattice-based, hash-based, isogeny, multivariate, and many. So people are trying to think about like different approaches from mathematics, and then hopefully we can find some nice math problems that can be used to derive crypto. So the current progress. So say we are already concluded the third round very recent, not very, but I would say just recently. So there are several schemes already selected for public key encryption and signatures. So one scheme was selected for public key encryption, that is Kyber, and for signature, there are 3 schemes. So Kyber and Dilithium and Falcon, they are, say, lattice-based. And there is another one, which is hash-based construction for signature. So say these 4 schemes will be standardized for the future, but there is still another ongoing efforts because so for the 4th round. So NIST, according to NIST, what they want is they want diversity. They don't want to standardize only 1 or 2 categories of post-quantum cryptography or crypto systems. We want more. So interestingly, during the study towards the fourth round, there are a lot of exciting, or some people might think of like heartbreaking news. So as the nature of sciences, many candidates were broken. So this includes a scheme called Rainbow, which is a multivariate signature, and another very popular, very say previously popular scheme called Psych, which is an isogeny-based public key encryption. And we expect more. Yeah, we don't know yet, but we expect more. And those two, say, schemes were the most, say famous not example, but instances of breaking crypto systems, because, say, the papers that break those systems got, say, Crypto Best Paper Award and Eurocrypt Best Paper Award. But anyway, there are still a lot of plausibly hard mathematical problems from lattice hash code, and still perhaps isogeny, but just not Psych. Okay, so now let's talk a little bit about my work at very high level and some applications. Okay, so my work focus more on the lattice-based cryptography, and as I said, this is one category of post-quantum cryptography. So because there are a lot of advantages like efficient operations, and this can be a foundation of many crypto systems. So to work with lattice-based cryptography, we need some mathematical, some hard problems. And particularly, this learning with errors is a very famous problem introduced by Regev. And it has attracted a lot of attention in both theory and practice. And we can derive many, say, new post-quantum candidates in theory. And this includes public key encryption, signature, and key exchange. And as I mentioned before, 3 variants are going to be standardized by NIST. So beyond the basic crypto systems, say lattice-based or learning with errors can be used to achieve computation on encrypted data, which is known as fully homomorphic encryption. And it can be used for outsourced computation. And according to DARPA core or DPRIVE, a program, it is cited, FHE fully homomorphic encryption is the holy grail to keep data secure while in use. So what is FHE? We consider this picture. So the user can encrypt her data and send that, outsource that to the cloud. Later on, she can request computation with a function f, and the server, without decrypting the data, and can just compute encryption of f of data and send back to the server, to the user. The user can later decrypt and learn f of data. So in this scenario, because the data, the encryption is never decrypted on the server side, so intuitively, the server cannot learn anything about the data. Okay, so this capability is known as homomorphic computation. And FHE has a nice application to multi-party computation. So it is an elegant solution to the classical, say, Yau's millionaire problem. So the idea is 2 parties, they hold inputs, 2 numbers, x and y. They need to determine which is larger without revealing what they are. And this has a lot of, say, applications in e-finance. For example, you want to compare numbers that are confidential. You want to, say, you want to two parties who want to bid for an item, but they don't want to reveal what their bids are. So to solve this problem, say Alice or one party can encrypt her input, and then the other party can homomorphically compute this f of x, where this f is the comparison function. Okay, so say Yale's millionaire problem was introduced back to the 80s, and now currently in 2020s we have say some more fancier applications, so which is say machine learning as a service. So FHE enables this private machine learning as a service. Consider the cloud holding some machine learning model Y, and the user holding some say image or some private data X. Can they achieve, say, can the user outsource analysis of private X without revealing X, and the cloud doesn't want to reveal Y? So the idea, fully homomorphic encryption, enables this application. The user just encrypts her private data, and the cloud just performs the homomorphic computation. Okay, so this F, the function F is the analysis using the model parameter Y. So this LWE is really a triumph for crypto theory. So under the hardness of LWE, which is learning with errors, the hard problem, there exists post-quantum public key encryption and signatures and a lot. And the theorem 2 says under LWE, there exists post-quantum fully homomorphic encryption for arbitrary functions. And there are a lot of more theorems, 3, 4, 5, much more. So in praise of LWE, a Gödel Prize was given to the inventor Regev in 2018. And the citation says, it served as the foundation of countless subsequent works. It revolutionized cryptography in theory and practice. And it is a simple yet amazingly versatile foundation for nearly everything. And many things were previously unimaginable until LWE. So is the problem solved? Because the theory says LWE implies everything. So we kind of know LWE offers solution in theory. And there is a huge gap between theory and practice. So this gap is beyond just engineering efforts. So kind of we need to expand and refine the theory so that the gap becomes bridgeable. So my work falls on this part. So we kind of want to determine the drawback a little bit. So yeah, so now I just talk about something very high level, because if we want to talk about drawback solutions, we can discuss for one more semesters. So now we know, I just present some kind of simple facts. We know plain LWE is not efficient. So we kind of want to know a little bit more why and how. So the why is, say, because it requires so large concrete parameters in computation, particularly large keys in general, and cumbersome noise in the sampling procedure. So as a consequence, say the plain LWE-based solution, say one submission to the NIST called a scheme called Frodo, was not selected as the finalist by NIST. So to improve efficiency, there are some high-level techniques people have considered. So people use other variants of LWE. for example, people consider algebraic rings, and we use other forms of errors other than the original forms proposed by Reagan. Of course, we can consider many variants, like however modification we want to make, but we need to go back to the fundamental question: are these variants hard? And beyond this, we also want to know, like, can we do more for the advanced capabilities from these variants as well? So my work, basically, I developed several algebraic techniques. And these algebraic techniques can be used to prove some useful variants of LWE is plausibly hard. And beyond, more than that, the algebraic techniques can lead to more efficient FHE methods. So in the kind of like the next maybe 5 to 10 minutes, I'm going to talk about a little bit, very high level, how algebraic techniques can lead to more efficient FHE methods. Okay, so we know FHE and F stands for fully. Okay, there is a core technique called bootstrapping. And currently, or previously, it was this technique is important, but it was slow. So my algebraic techniques can lead to more efficient bootstrapping. So now we are going to talk a little bit about what bootstrapping means in a very high level, and I hope after my presentation, you will understand what bootstrapping is. So we know all FHE ciphertexts contain some sort of noise and some basic operations. For example, if you want to perform addition, multiplication, or NAND, they are really rather fast. And computation, if we want to perform computation, we need to increase the noise in the ciphertext. So at some point, noise would become too large so that computation cannot proceed. So consider this example of electric car. So every electric car associated with some battery level. So you can think of this as noise level. So initially, a ciphertext is very clean. It does not have a lot of noise. So this corresponds to high level of battery. And during computation, the noise increase, or like, and you can think of this as the battery level decreases. And at some point, you might reach a point where the ciphertext is somewhat noisy, but not too noisy. And in this scenario, in this case, the computation cannot further proceed, because if you compute further, you deplete the battery, and then in this case, the decryption will fail. Okay, so in order to proceed computation, we need a way to clean noise. So this is called bootstrapping. And bootstrapping currently is significantly slower than the other basic operations. And this is really the bottleneck. So pictorially, you can think of this. So you have a ciphertext that has very low battery, and bootstrapping procedure is kind of a charging procedure. And after this charging procedure, the ciphertext will become, say, the battery increases, okay, so that the computation can be proceed further. So currently, the bootstrapping framework was introduced by Gentry. So in his breakthrough paper, So the idea is we need some kind of bootstrapping key, which is an FHE encryption of its secret key. So something like this. And given an input encryption of X, which might be somewhat noisy, we define a function FCT, which is decryption on the ciphertext using the input. So by homomorphically compute this function, you will get encryption of FCT of SK. And by correctness of the decryption, this would be X, which is the original input. So the homomorphic computation, the process, it also incurs error, E prime. So we hope the E prime be as small as possible. So you think of like, you can say pictorially, you can think of this as the charging procedure will also cost you, say, battery. So you want to you want a more efficient charging procedure that causes the battery loss as small as possible. So hopefully, at the end, we still have a lot of remaining battery so that we can proceed further. Okay, so now, say initially, the bootstrapping was really slow. It takes 30 minutes to bootstrap one ciphertext. And there are significant improvements over the past few, say, 10 years. So one improvement was, say, consider, say, the second generation of FHE. We have large ciphertext, and but this approach supports SIMD, which is single instruction, multiple data. And for the third generation, we have small parameter and fast bootstrapping. Okay, as I show in this picture, this can be bootstrapped within, say 30 milliseconds. However, the third generation, the small parameter approach doesn't support SIMD. Okay, so my mathematical framework supports small space and SIMD simultaneously. So the open question is like, we want to optimize the framework, more refined math, and maybe determine concrete parameters, and maybe implementation and deployment. Okay, so finally, let's talk a little bit about my vision and some future opportunities. So one thing is about core FHE. So this is also very important and very exciting. So whether to further develop more algebraic techniques to improve the theory. And also, say, we want to expand the existing FHE libraries. Say, for example, and there are a lot of, say, collaboration say, opportunities with hardwares, for example, ASIC, multi-core CPU, high-performance computing, and GPU computing. And another direction is applications to machine learning. So this is, as we demonstrated in the very beginning, private machine learning as a service, whether we can develop an architecture, computational architecture that is friendly for both FHE and also machine learning. And another future direction is like there are a lot of advanced crypto capabilities like zero knowledge proofs, anonymous credentials, which I haven't introduced today, but definitely there are a lot of future chances that we can talk about those ideas. And hopefully, we want to develop efficient post-quantum privacy enhancing technologies for the future. Okay, so the vision is, say, we know that LW implies everything. This is extremely successful theory. And we want, say, hopefully from this year, from today, and maybe like a couple years, we are making a lot of efforts to make this theory a practical reality. So this would include develop new theory, refine existing theory, and we also need to continue bridging the gap between theory and practice. So thank you very much for listening to my talk, and I think we still have a couple minutes for more for questions, and yeah.
Thank you very much, Fenga, for that excellent presentation. And we do have, you are right, some time, not a whole lot of time, but some time for questions. Thanks for keeping this at a very high level and accessible and very nice slides to follow along. Does anybody have, and I think you should feel free to unmute yourselves and ask questions, or you could put them in the chat. I think we can take a couple questions with the time we are left with. And thanks, James, for putting the link for the survey on the chat. Students, when you finish this, take a few minutes to fill that out. That's helpful. Does anybody has a question for Fenga? Maybe while people think for a question, I could ask you one broad type of question, right? Or is there anything you see on the chat?
I think there is someone raising hand.
Who is that? I don't know.
Noah?
Oh, hi. Yes.
Okay. Yeah. Please
go ahead and ask a question.
Okay. Do you know of any crypto systems that are currently out there in applications and programs that are ubiquitous that are currently resistant to the quantum attacks?
So for the standardization, so before standardization, people have already started to build their or write codes, implement their several post-quantum candidates they think that are secure. Okay, so say for those lattice-based encryption and also isogeny or code base. So there are a lot of different teams, even before post-quantum computer, before the NIST, they have already started the process because that's their research. But but before the standardization process, maybe you build your own system, you choose your own parameters, and I choose my own parameters, and so it's a little bit hard to to unify everything. So that's why this standardization process is about, so that we have a standard where everyone can follow. But to answer your questions, I would say different research teams have already implemented different post-quantum candidates before, but those candidates are maybe still in the research phase, not in the deployment phase. So I won't say they are in use, but future future applications, they will definitely use the standardized ones.
Thank you.
Does anybody has other questions? If we see, I'm going to ask the question I was going to ask you, Fenga.
Sure.
So you've got these things you have between before you get to bridging the gap to the engineering sort of things, implementation-wise, a couple things in theory and refining and coming up with new. For if traditional cryptography, if we look at it, you look for the hard problems because they will be difficult to do, and they will be candidates for doing good ways to secure. Basically, at a very high level, we can think of them like that. And for that, we look for hard problems, and we would need ways to think about what it means to be hard, and we have the theory of computation, things that would tell us when a problem is hard. When you get to this post-quantum computing, are those things that we know in traditional and the way we have models for defining hardness, are they good enough, or do we have to even have a model for this new scenario? If you just can comment at a high level on that.
Okay. Let me comment that the traditional complexity theory still applies. So we defined MP class, P space. Those research they are still there, and because of this quantum computing, we have like a new a new class called BQP, bounded quantum. It's like BPP, this bounded probabilistic polynomial time. So bounded, say quantum polynomial time, probably right. So we kind of, because of quantum computing is a new model of computation, because we don't think classical computing Turing machine can capture that. So we need a new model for quantum computing, and we study the complexity of those quantum models. And currently, for those hard problems, and say if we want to ultimately prove them to be hard, this would imply P is not equal to MP. Which we have no idea how to prove still until today. So so people are trying to do a little bit, we compromise a little bit. So we focus on the best attacks to those say hard problems. And if those best attacks cannot solve the problems, we conjecture that it to be hard. So this is a little bit, say, fortunate and unfortunate because of the limit of our human knowledge. So currently, this is what the best we can do.
Right. Thanks a lot. We are a couple minutes over. I think I have not seen. I'm sure people would have questions, but they could look back at your slides and reach out in other ways. Thank you very much, everybody, for joining us today. Thank you very much, Fenga, for making the time and giving this nice, very good lecture on difficult topics, but kept at a very high level. So you did an excellent job on that. Next seminar will be 2 weeks from today, and you'll get details later on. But for now, don't forget to fill out the surveys, and I think we will stop here. Thanks again.
Okay, thank you very much. See you soon.